Hi guys, today we're going to be talking about geometric sequences. Now the basic definition of a geometric sequence is one in which each term is a constant multiple of the preceding term. This constant is known as the common ratio, or R. All geometric sequences can be written in one of two ways, either explicitly as t subscript n, the nth term, is equal to a times r to the n minus 1, or recursively as Tn, the nth term, is r times the previous term, Tn minus 1. Okay, so now we'll take a look at an example of a geometric sequence. So here we see the sequence 3, 6, 12, 24, 48, and so on. And as we can see, each term is double the one before. So 3 by 2 is 6, 6 times 2 is 12, 12 times 2 is 24, and 24 times 2 is 48. So that makes this a geometric sequence with common ratio 2. And if we start to look at each of the terms, we'll see that the first term is 3, the second term is 3 by 2, the third term is 3 by 2 by 2, 3 by 2 squared. The fourth term is equal to 3 times 2 times 2 times 2, or 3 times 2 cubed. And the fifth term that we have there is 3 by 2 by 2 by 2 by 2, or 3 by 2 to the power of 4. And we can continue this pattern and realize that the nth term is therefore going to be 3 times 2 to the power of n minus 1. So if we want to get to, say, the 16th term, we have to start with our first term 3 and multiply by our common ratio 2 15 times. This gives us our explicit formula for this particular sequence, but we can also write our recursive formula as t subscript n, the nth term, is equal to 2 lots of the previous term. So each term is double the one before. And of course, when we're defining our sequence in this way, we also have to state one of the terms in the series. So we can state, in this case, the first term, a equals 3. We can then generalize this to any particular sequence. If we have the sequence term 1, term 2, term 3, term 4, etc., where each of those terms is r times larger than the one before, then we can write in general that the equation is term n equals a, the first term, r to the n minus 1, or recursively that Tn equals r times Tn minus 1. And what we can do then as well is we can actually redefine this formula in terms of any other term. So if we were to, say, start at term 5 and we wanted to get to term 7, we would obviously have to multiply by the common ratio twice. And we write that for any general term as, to get from term m to term n, we need to know how many lots of the ratio we need, how many difference there are between the two term numbers. And using this formula, you can calculate any term of a geometric sequence if you know one term and the common ratio. We can also rearrange this formula to give us r is equal to Tn divided by Tn minus 1. And all that's saying is you can calculate the common ratio by taking any term and dividing it by the term previous. To finish, we'll look at one last example of a geometric sequence. Here we have the sequence 8, 4, 2, 1, half, etc. And we can easily see that each term is half the term before. And you'll notice that I've written that as multiplying by a half rather than dividing by 2, because we always need to define a geometric sequence in terms of its common ratio, or the number that is multiplied by the previous term to get the next term. So for this sequence, the explicit formula would be that the nth term is 8 times half to the power of n minus 1. And it has a common ratio of a half. We can also write the recursive formula as Tn equals half of Tn minus 1, or Tn minus 1 over 2, with the first term